Hello, my name is Chris Fodop.
And my name is David Kim. Welcome to our tutorial video on the ideal gas law.
In this tutorial, we are going to conceptually explain the ideal gas law and show how to apply its equation to mass balance problems. The ideal gas law relies on three key assumptions. First, that the gas consists of a large number of molecules in random motion, obeying to Newton's law of motion. Second, the volume of the molecules is negligibly small compared to the volume occupied by the gas. And third, intermolecular interaction forces are negligible. Although most gases don't have these properties, the behavior of real gases is described quite closely by the ideal gas law at sufficiently high temperatures and low pressures, when relatively large distances between molecules and their high speed overcome any interaction. However, if the gas is near condensation point, it will not be considered as ideal.
Now that we have a clear understanding of what an ideal gas is, let's look at the equation that is used in accordance to the assumptions for gases, the ideal gas law, which is PV equals nRT. In this equation, P stands for absolute pressure, V stands for volume, N stands for the number of moles, R stands for the ideal gas constant, and T stands for absolute temperature.
To give you a better idea of this concept, imagine a piston inside a cylinder. If you lower the piston, the volume inside the cylinder would decrease, therefore increasing the pressure due to an increasing rate of collisions of molecules against the wall of the cylinder. An important conclusion we can make from this relationship is that when solving for mass balance problems, volume is not necessarily conserved. Similarly, increasing the temperature inside the cylinder will increase the kinetic energy of the gas molecules, hence increasing the pressure.
Now about the gas constant. You may probably know this to be 8.314 newtons over meters squared times meters cubed all over moles times Kelvin. And yes, you would be correct, except for one thing. It would only be correct for, let's say, if the rest of the equation was also using pressure in the units of Pascal, which is newtons over meters squared, volume in the units of meters cubed, N in the units of moles, and T in the units of K. In any other case, you would either have to change the other information into these units or use a value of R that corresponds to the different units. This basic principle of having a corresponding units is called dimensional homogeneity, which directly states that equations must be dimensionally consistent. For me, however, to better understand this term, it helped to imagine the constant to be a key and then the rest of the equation to be a lock. You will not be able to use a key on a lock that does not have the same shape and size as one another.
One technique you will find very useful when solving mass balance problems for different processes is the ratio of ideal gas law, which is P1 V1 over P2 V2 is equals to N1 R T1 over N2 R T2, where the subscript 1 represents the initial state. And the subscript 2 represents the final state. When using this technique, the ideal gas constant corresponding to the problem can be ignored because the constant will be the same in both the initial and the final state.
Here is an original example to help you better understand this law. It's your little brother's birthday party and you rented a tank containing 2 liters of helium at an absolute temperature of 300 degrees Kelvin and an absolute pressure of 1.5 atmosphere for the balloons. What will be the volume of helium if both the absolute temperature and absolute pressure were changed to 350 degrees Kelvin and 1 atmosphere respectively? For this problem, referring back to the ratio of ideal gas law mentioned before, which is P1 V1 over P2 V2 is equal to T1 N1 R over T2 N2 R, we can simply readjust it to solve for what we are looking for, which is in this case the new volume. Since the number of moles and the ideal gas constant for this ratio is exactly the same, we can cross them out, leaving the equation to take the form of V2 is equal to P1 V1 T2 over P2 T1. Now, using the given information of the initial volume, the initial temperature, the initial pressure, the final temperature, and the final pressure, we can solve for our only missing variable. After plugging those in, we get our final answer to be 3.5 liters.
Let's apply what we have just learned to mass balance problems. Pause the video for a few minutes and read the problem thoroughly. First, let's start by establishing the characteristic of our system. Because material flows into and out of the system boundary, our system is open. In this problem, acetaldehyde is converted to ethanol, so the system is reacting. Since there is no change in mass entering and exiting the system, we can assume that the system is at steady state. And because the given temperatures are relatively high and pressures low, we can assume that our system is operating on ideal gas law, meaning that PV is equals to nRT. Next, one thing you should notice is that the pressures given in the problem are gauge pressures. So we need to add atmospheric pressure, which is 14.7 psia, to the relative pressures in order to find the absolute pressures. We are being asked in this problem to find the meter cubes of C2H4O recycled per meter cube of C2H4O fed. So let's start by performing our degree of freedom analysis around the reactor and the separator. We do have 5 unknowns, which are C2H4O, C2H4O, C2H5OH, H2, and H2. One extent of variation, because there is only one reaction occurring. 3 mass balance equations, because we have 3 species. 1 degree of completion, which is right here. 1% excess, which is right here. So that gives us 5 plus 1, which is 6. And then 3 plus 1, which is 5. So our degree of freedom is equals to 1. Therefore, we need to set up a basis. We set up our basis to be 1 meter cubes of C2H4O fed at 250 degrees Celsius and 34.7 psia. Next, using the ratio of ideal gas law, we can find the number of moles of C2H4O fed. So we have P1 V1 over P2 V2 is equals to N1 R T1 over N2 R T2, where the subscript 1 represents the standard temperature and pressures, and the subscript 2 the actual conditions. And in this equation, we are solving for N2, which is equal to 1 mole multiplied by 1000 liters, because we assume our basis to be 1 meter cubes, divided by 22.4 liters, times 273 Kelvin, which is the inertial temperature, divided by 273 plus 250. And we multiply this by 34.7 psia over 14.7 psia. And we found N2 to be equal to 55 moles. Which in this case is 55 moles of C2H4O fed. Now, we can write our general mole balance equation, which is accumulation is equals to in minus out plus generation minus consumption. And we assume our system to be at steady state, meaning that accumulation will be equal to 0. And there's no product being generated in the system, so generation will be equal to 0 as well. Next, we can write our mole balance for C2H4O around the reactor and the separator. We know that the degree of completion is a fraction conversion of the limiting reactant. And in this problem, we know that there is 10% excess of H2, meaning that C2H4O will be the limiting reactant. Therefore, the number of moles entering the system in the C2H4O balance will be 55 plus R, minus the number of moles out, which will be R, minus the consumption, which will be the fractional conversion of the limiting reactant, which is 0.6, times 55 plus R. And we end up with having R being equals to 36.66 moles of C2H4O recycled. Now that we have the number of moles of C2H4O recycled, we need to find the meter cubes of C2H4O recycled. And in order to do that, we need to consider the temperatures and pressure changes. Meaning that the problem told us that to find the meter cubes of C2H4O recycled at 300 degrees Celsius and 25 psij. So in this case, we are going to use the ratio of ideal gas law one more time in order to find the meter cubes of C2H4O recycled at those temperatures and pressures. And we find it to be 0.638 meter cubes of C2H4O recycled. Next, to find our problem, we have to calculate the meter cubes of C2H4O recycled per meter cubes of C2H4O fed. So we already know the meter cubes of C2H4O recycled, which is right here. We assumed our basis to be 1 meter cubes of C2H4O fed. Therefore, all we have to do is 638 meter cubes of C2H4O recycled over 1 meter cubes of C2H4O fed, which is equals to 0.638. And that's our final answer.
In conclusion, the ideal gas law is a very important concept that can help solve various mass balance problems that involve gas substances. A few key concepts to remember when applying this equation is to first, make sure that the gas can be assumed to be an ideal gas. Second, that the units are corresponding to one another. Third, to know how and when to use the ratio of ideal gas law. And finally, to know that the volume is not necessarily conserved. We hope this tutorial was helpful in your understanding of how to use the ideal gas law in solving mass balance problems. Thank you!